All right, in chapter 10, section 3, we're going to talk about the integral test. What we're trying to do here, whenever we have a series or a sequence, we always want to test to see, does it converge or diverge? That's the question which we always want to ask about a series. So here we'll examine series with non-negative terms to see if they converge. In the long run. Spoiler alert. They will, as long as the partial sums are bounded. All right, so the first thing let's look at. Non-decreasing partial sums. So given a sequence where n equals 1 to infinity of a sub n, where each term is positive, it's greater than or equal to 0. Then the partial sum will be greater than 0. And each successive partial sum will be greater than its predecessor. In other words, what that says is this is our partial sum of the first one is going to be less than or equal to partial sum of the second. It's going to be the third, partial sum of the third. It's going to be less than partial sum of the fourth, and so on and so forth. And it keeps on going for infinity. So that's what we're going to look at. Here's a corollary to theorem 6. A series from n equals 1 to infinity of a sub n with all its terms being non-negative will converge if and only if its partial sum are bounded. Above. In other words, it has to have a number that it has to be reached to. So if the partial sum is less than some number, then it'll be a finite set. Example 1. says, consider the harmonic series bounded from above n equals 1 to infinity of 1 over n. So when n is 1, you get 1. When n is 2, you get 1/2. When n is 3, when n is 4, and so on and so forth, you get 1 over n, and keep on going to infinity. The series diverges because there's no upper bound. Excuse me. There's no upper bound. It keeps on going. You can take a look at this. They're saying that we have 1 plus 1/2 is 3/2. And you have 1/3 plus 3/4. That's going to be 7/12. Then you have the next set and next set. So it keeps on getting larger and larger and larger and larger. It keeps on increasing. So let's introduce the topic of this section. The integral test. It is used with series that are related to harmonic series but whose nth term is 1 over n squared and not 1 over n. Let's look at example 2. The sequence summation of 1 goes to infinity of 1 over n squared. So at 1, it's 1. At 2, it's 1/4. At 3, it's 1/9. At 4, it's 1/16, and so on and so forth. Does it converge? To determine whether it converges, we can compare it with the terms of the integral from 1 to infinity of 1 over x squared dx. The integral of 1 over x squared from 1 to x infinity is -2 it's -1 over -1. -1 over x from 1 to infinity. So looking at 1 over x squared looks like this from 1 to infinity. So we're looking at these rectangles. So we get here, we have our partial sums are 1, 1x is 1, 1x is 2, this is 4. So this is 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, 1 over x squared, each of these terms are less than the corresponding function. F of 2 plus f of 3 plus f of 4, f of n. Leave the first term alone. And these, we get the integral from 1 to infinity of 1 over x squared dx. One plus the integral is 1. See, -1 x this goes to a 0. This becomes a plus. So we see that the series 1 over n squared is bounded above by 2. So it converges. All right, let's see what the next one is. Look at theorem 9. The integral test. Let the sequence a sub n be a sequence of positive terms. Suppose a sub n is equal to a function at n, where f is a continuous, positive, and decreasing function of x for all x greater than equal to some n. Then the series summation of n equals capital N goes to infinity, a sub n, and the integral from n to infinity of f of x either both converge or both diverge. Example 3. Show the P series converges if P is greater than 1 and diverges if P is less than equal to 1. To begin with, a P series looks like this. Its summation as n goes to 1 to infinity of 1 over n to the power p. If p is greater than 1, it converges. If p is less than equal to 1, it diverges. So here's a solution. A. I'm looking at p is greater than 1. So f of x is equal to 1 over p, n to the power p. It's greater than 0 for all terms because n is positive. So whatever p is becomes, and p is greater than 1, so it stays down there. And as p goes to infinity, it decreases. So it's greater than 0, it decreases, and it's continuous. It matches the 3 conditions that we need. So we can do the integral of 1 to infinity of 1 over np dx is equal to the integral of 1 to infinity of n to the power negative p r x, since we're dealing with dx. So that becomes the limit as n goes to infinity of add 1. So we get negative p plus 1 from 1 to n. limit as n goes to infinity of this. You can take out, that's a constant term. So what we have left is x to the power p minus 1. One over negative p plus 1. The limit as n goes to infinity of n p minus 1 minus 1 over 1 p minus 1. So as p goes to infinity, as n goes to infinity, this one goes to 0. Doesn't matter what that is, it stays 1. So it's minus 1. So this becomes negative 1 over negative p plus 1, which is 1 over p minus 1. So it converges. Example 4. This summation, n goes to 1 to infinity, 1 over n squared plus 1. No. It is not a p series. But it converges by the integral test. So our f of x is equal to 1 over x squared plus 1. Does it match the three conditions? Yes. This can never be 0, so it's greater than 0. As x goes to infinity, it decreases. And there's no discontinuities and is continuous. So it meets the three conditions. So the integral from 1 to infinity of 1 over x squared plus 1 dx is equal to the limit as n goes to infinity. The integral of this is the arc tangent of x. So the limit as n goes to infinity, the arc tangent of n minus the arc tangent of 1. Now, as n goes to infinity, remember, arctan is bounded from negative pi over 2 to pi over 2. And since it's going to infinity, that means it's approaching pi over 2. Where is the arctangent equal to 1? What angle does the sine over cosine equal 1? At 45 degrees or pi over 4. There's 2 pi over 4 minus pi over 4 makes it 1 pi over 4. It's bounded, so it converges. Example 5. Converge or diverge. How much more requirement? A. We'll do both of them here. B. A is summation of n equals 1 to infinity of n e to the power n squared. Summation of n equals 1 to infinity of 1 over 2 ln. So we have the summation from 1 to infinity of n e n squared dx, which makes it x e negative x squared. One to infinity of x over e to the power of x squared dx. So we said u is equal to x squared. Du is 2x dx. So du dx is equal to 2x. Okay. When I plug in 1 in there, it's 1. So it remains the same bounds. Okay, so since this is x dx, I need a 2, so I got to put a 1/2 out in front. Right there. So this becomes du, and this becomes eu. Take the limit as n approaches infinity. The integral of e negative u is negative. Oh, I should have finished in half right there. So it becomes negative e to the negative u from 1 to infinity. The limit as n goes to infinity of negative 1/2 over EU. The limit as n goes to infinity of so we go from negative 1, 2 to the power e to the infinity, or e to the n, minus negative 1/2 e to the power 1. So that goes to 0. That becomes positive. So I have 1 over 2e. So the series converges. Do the same thing here. So 1 to infinity of dx over 2 ln x. So u is equal to ln x. E to the power u is equal to x. So dx is equal to the e u du. All right, so we have from 1 to infinity. Dx is eu du over 2 to the power u. So u equals ln 1, u equals 0. So it's e over 2 to the power u du. The limit as n approaches infinity, the integral of eu over 2 becomes 1 over ln e over 2. Times e over 2 to the power u. Makes it the limit as n approaches infinity. 1 over ln e to the 2. E over 2 to the power infinity minus e over 2 to the power 0. This is a constant, so it stays out in front. E over 2 to the power infinity minus e over 2 to the power 0. And so that goes to 0, that goes to 1. No, it then goes to infinity. This goes to infinity. So we have infinity over ln e over 2, which goes to infinity. So the series diverges since it's not bounded on top. Error estimates. So given any sequence, summation of a sub n, where a sub n is greater than 0, and convergent by the integral test. We want to estimate the size of the remainder R, where R is the difference between the total sum S and the partial and the nth partial sum S sub n, where R is equal to the S minus Sn, where it's just going to be the terms a n plus 1, a n plus 2, n plus 3, and so on and so forth. Because all of the a sub n's up to a sub n cancel out. What we're left with is the difference. So first off, we figure out the lower bound for the remainder R. Compute the first off, you can compute the sum of the areas of the rectangles with the area under the curve y equals f of x for all the x's greater than 0. Then R sub n is a sub n plus 1 plus a sub n plus 2 plus a sub n plus 3 plus everything else. So that remainder is going to be greater than n plus 1 to infinity of our function dx. So this defines our lower bound, the integral of the function from n plus 1 to infinity. The upper bound from R sub n is a sub n plus 1, a sub n plus 2, a sub n plus 3, plus, it's going to be less than or equal to the integral from n to the infinity of f of x dx. That's the upper bound. So we have to figure out, when we figure out the upper and lower bounds, that's what we're going to look at. So now we're going to talk about the bounds for the remainder in the or of the integral test. If a sub n is a sequence of positive terms with a sub k equal to f at k, where f of x is continuous, positive, and decreasing for all x larger than n. And the summation of the sequence converges to S. The remainder, R sub n, is equal to S minus the partial sum S. And satisfies this condition. The lower sum, the integral of the lower sum, dx, is less than the remainder of n, less than or equal to the upper sum, the integral of f of x dx from n to infinity. Also, if we add up the partial sum S of n, well, if we add the partial sums S of n to both sides, we get S sub n plus the integral of n plus 1 to infinity of f of x dx is less than the complete sum n to infinity of f of x dx. So that brings us to example 6. Estimate the sum of 1 over n squared with n equals 10 we use this integral. All right, so we'll use that. So we have 1 n to 1 over x squared dx is equal to the limit, since it's the upper bound, n, b goes to infinity, 1 over x squared becomes the limit as b goes to infinity of negative 1 over x from n to b. So we have to integrate that, which becomes that. So we take the limit as b goes to infinity of negative 1 over b minus negative 1 over n. B goes to infinity, negative 1 over b plus 1 over n. As b goes to infinity, that goes to 0, so we're left with 1 over n. So our equation n to infinity so that becomes, remember, n equals 10, so we have S10 becomes 11 or 10 plus 1 S of 10 to infinity remember, since we figured out this is 1 over n, this is going to be 1 over 11 S10, this is going to be 1 over 10. That's because we figured out that's 1 over n. Also, S sub 10 is summation of n equals 1 to 10 of 1 over n squared, which is approximately 1.54977. So we got 1.54977 plus 1 over 11 is less than equal to S is less than 1.54977 plus 1 over 10, which gives us approximately 1.64068. 1.64977. And that's our solution. All right. Thank you much. See you next time.